Okay, so today we're going to continue with the second part of chapter 9. And so remember that chapter 9 is all about mathematical relations or abstract relations between different types of objects. So before we move into the newer material, I just wanted to point out a small mistake in the last lecture. And so in the final example, when we were talking about transitive relations, in the previous lecture, I had forgotten to include the relation 2, 4. And so notice that since this relation was supposed to be transitive, well, it contains 2 is related to 3, and 3 is related to 4. And so therefore, since it's transitive, we need to, if we want it to be transitive, we need to have 2 related to 4. And so I accidentally left that out. Right, so I just wanted to update that in the video. I sent out an email as well, but I wanted to update it in the video as well in case you missed the email or were confused by that example. Okay, right, and so remember at the end of the last lecture, in addition to transitive relations, we also talked about symmetric relations, right, where a relation is symmetric if whenever A is related to B, that implies that B is related to A. And we also talked about reflexive relations. Now, a relation is reflexive if any element of the relation is related to itself, right? So we have reflexive relations, meaning every element is related to itself. Symmetric relations, meaning if AB is in the relation, then in the reverse order, BA is also in the relation. And then finally, transitive relations, which have this transitivity property, right? If A is related to B and B is related to C, then A needs to be related to C, right? So sort of the fact that A is related to B and B is related to C connects A to C, and we require that A is related to C for it to be transitive. Right, and so if you look at a particular relation that has all three of these properties, this is something that's known as an equivalence relation. And so the rest of this lecture will all be about these things called equivalence relations. Right, and so here's the proper definition. So let's say we have a set A and a relation R on that set. Then the relation is said to be an equivalence relation if it is reflexive, symmetric, and transitive. And so what's a good way to think about this? Well, if you have a relation that's equivalent, it gives you a nice way to break up the set A into groups of different elements, which we think of as being equivalent. And so what does it mean? Formally, for them to be equivalent, well, they're related to one another by whatever relation we choose to work with. And so before we go into more detail and more examples, just sort of think about what does it mean sort of in common language for different things to be equivalent, right? If we want to have some way of breaking up a larger set into smaller pieces which are all equivalent, well, what does it mean for one element of the set to be equivalent to another in common language? Well, we would expect that any element should be equivalent to itself because it's the same thing, right? And also, well, if A is equivalent to B, then we would expect B should be equivalent to A as well, right? So that's the symmetric property. And finally, if some element A is equivalent to some element B, and some element B is equivalent to some other element C, then we would expect that A should be equivalent to C also. And so this is the reason why we're requiring the reflexivity, symmetry, and transitivity in order to sort of come up with a mathematical notion of what it means for them to be equivalent. Right? And so now let's sort of dive into more details. Right, and so first, just a little bit more notation, right? So let's say our relation R is an equivalence relation, and we know that two elements of the set A and B are related. Well, we'll also write A is equivalent to B in this way using this notation. Right? So this is, when you see this notation, it's usually used to mean A and B are equivalent with respect to the fixed relation, right? And we would say A is equivalent to B. Right, so one quick example. So let's suppose that my set A is just the set of all residents of the United States, all people living in the US. And we'll define a relation R on the set A by saying that a person A is related to person B if they live in the same state. Right? And so it's not hard to check that this is an equivalence relation. Well, how do we prove that the relation is an equivalence relation? We have to show that it's reflexive, we have to show it's symmetric, and we also have to show that it's transitive. And so let's just fix 3 people in the set. So these are just 3 arbitrary residents of the United States. Well, of course, for any A in the set, A is related to itself because person A lives in the same state as themselves. Right? It's kind of redundant or sort of obvious, and therefore this relation is very clearly reflexive. It's not always the case that it's going to be obvious that a relation is reflexive. I'm just saying for this particular relation, it's clear that it's reflexive. Right, now let's suppose, right, so this proves it's reflexive, so now let's prove that it's symmetric. How are we going to prove that it's symmetric? Well, we have to show that whenever A is related to B, then B is related to A, right? We have to show that we can flip the order in the relation. So in order to show that, let's suppose we have A and B in the set, and suppose A is related to B. Well, what is the definition of the relation? It says that because A is related to B, A lives in the same state as B. Well, if A lives in the same state as B, then of course B lives in the same state as A. And so if we connect this statement back to the definition of the relation, that means that B is related to A. And therefore, right, so since this works for any pair A and B, assuming that A is related to B, we prove that B is related to A, it follows that the relation is symmetric. Right, and so once again, sort of when you unwind the definition here, this is a very easy argument to show that this relation is symmetric. So this example is in some sense a little bit too easy, but I think it's a good way to outline like how you would prove a relation is symmetric. For more complicated relations, maybe this part is going to be a little bit harder, depending. Okay, and so we've proved reflexivity and symmetry, so now we just need to prove transitivity. And so how do you prove that the relation is transitive? Well, I want to show that if A is related to B and B is related to C, then that implies that A is related to C. So I just have to fix 3 elements in my set, in this case, 3 people, person A, B, and C. And I'm assuming that A is related to B and assume that B is related to C, and I need to use these 2 pieces of information to show that A is related to C. And so once again, if we unwind the definitions, what do these 2 things say? Well, the first bit of information says that A lives in the same state as person B, and the second piece of information says that person B lives in the same state as person C. Well, if person A lives in the same state as B and B lives in the same state as C, then of course A has to live in the same state as C, right? And so therefore A has to be related to C, and so we've shown that the relation is also transitive. And so now these 3 pieces of information together imply that the relation is, we've proved that the relation is an equivalence relation in the sense of this definition up here. Great. Okay, and so another example, which is maybe a little bit more mathematical. So this is, we're going to be talking about congruence classes of integers. So this is a certain type of equivalence relation which shows up all over the place in number theory and also in computer science applications of math and computer science. And so what is the congruence class of an integer? Well, we'll begin by defining a certain relation on the set of integers. And so we're going to fix some integer m which is bigger than 1. And let's suppose A and B are two other abstract integers. Right. And so we're going to say that an integer A is congruent to an integer B mod m if when I look at the difference A minus B, then this is divisible by m. Or equivalently, A and B are equivalent mod m or congruent mod m if A minus B is some multiple of m, right? So in terms of formulas, that means that A will be congruent to B mod m if when I look at the difference between these 2 numbers, I get some multiple of m, right? So A minus B is equal to k times m for some k and z, or some integer k. Right, and so this is one particular way of defining some kind of congruence or equivalence between integers that turns out to be very useful for reasons you'll see in the future if you take more math classes or computer science classes, or maybe you have seen this before, depending on your background. Right, and so since this definition is kind of, there's a lot of information here in this definition, so the shorthand notation to make this sort of easier to write out, we'll usually say A with this sort of modified equal sign B mod m. And so the way you read this out is A is equivalent to B mod m, or A is congruent to B mod m. And so this notation is just shorthand for what's in the lines above it. Right, and so this means that A and B differ by some multiple of M. Right? And so we're going to use this particular construction to define a relation R on the set A, where A is going to just be the set of all integers. And so what is our relation? Well, we'll say A is related to B if and only if A is congruent to B mod M. Right? And so this relation depends on the choice of M. So maybe I should really be writing R sub M here to indicate that it depends on M, but it's hopefully clear from the context in this case. Right, and so it turns out that this notion of congruence mod M is an equivalence relation. And so we'll prove this on the next slide. Right. So what do we have to prove, right? Remember, we have to check three things. We have to check that this relation is reflexive, symmetric, and transitive. And so let's suppose we fix some three arbitrary integers. We first want to show the relation is reflexive. So we need to show that every single A is related to itself. But remember, what does it mean for A to be congruent to itself mod M? It means that when I look at the difference A minus A, then that's an integer multiple of M. But A minus A is equal to 0, and of course 0 is an integer multiple of M, right? Because 0 is 0 times M. And so therefore A is congruent to itself. So reflexivity is straightforward. So next we want to check that this relation is symmetric. And so how do we show it's symmetric? Well, we have to assume that I have two elements, A is related to B, or A is equivalent to B mod M. And we need to show that we can flip this around, right? So I need to show that assuming this, that B is equivalent to A mod M, assuming that A is equivalent to B mod M. Well, what does it mean for A to be congruent to B mod M? It means I can find some integer K such that A minus B is equal to K times M, right? A minus B is a multiple of M. And I want to relate this to the reverse order, or to B minus A. Right, well, we'll notice that if A minus B is equal to K times M, then B minus A is equal to minus K times M. And clearly, if K is an integer, then minus K is also an integer, right? So B minus A is also an integer multiple of M, and therefore B is congruent to A mod M. So there's not, I mean, the technical work we're doing here is hopefully very easy. It's just a matter of like writing down the definitions precisely and making sure you're checking the right things. And then the proof in this case is not so hard. Right, and so we just showed that if A is congruent to B mod M, then B is congruent to A mod M, and therefore B is related to A, which implies that the relation is symmetric. Right, so we've proved it's reflexive and symmetric, and finally we need to check that it's transitive. Right, and so how do we check that this is transitive? Well, we have to assume that A is congruent to B mod M and B is congruent to C mod M, where A, B, and C are just arbitrary integers. And then we want to show that these two together imply that A has to be congruent to C mod M. Right, and so what we're going to do is just refer to the definition, because there's not much else we can do. Right, so what does it mean for A to be congruent to B mod M? It means that A minus B is equal to some integer K1 times M. And what does it mean for B to be congruent to C mod M? Well, it means that B minus C is equal to some integer K2 times M, right? So our assumptions imply these two equations, right? And so what do we want to do? Well, we want to show that A is related to C. So we want to show that if I look at A minus C, then that's an integer multiple of M. And so, well, again, there's only really one thing we can do given this information, right? And so notice I want to show that this quantity A minus C is an integer multiple of M. What I'm going to do is write it in terms of the information that I know, right? So I know A minus B and I know B minus C. Well, I can break up A minus C as A minus B plus B minus C, right? Because the minus B and positive B will cancel out, and I'll just get A minus C again. And then if I plug in these two equations into the parentheses, I get that A minus C is equal to K1 times M plus K2 times M. And so, of course, I can factor out the M and get that A minus C is K1 plus K2 times M. Now, K1 plus K2 is an integer, since K1 and K2 are both integers, and therefore it follows that A is congruent to C mod M. and hence A is related to C. And so this completes the proof that the relation is transitive, and so therefore it's an equivalence relation. Okay, and we'll do one more example of some relation that will prove it is an equivalence relation. And so in this example, let me set A to be the set of all finite strings consisting of say numbers and letters in the English language, right? English alphabet, right? So the strings are finite strings, although they can have arbitrary length, and they're made up of just numbers and also letters from the English alphabet. And so I'm going to define a relation on the set by saying that for two strings A and B, A is related to B if the two strings are the same for the first 1 million characters, right? So you want to think of A and B as some finite string of letters and numbers. I'll say A and B are equivalent if they agree up to the first 1 million characters, and then after that they can be different, but I'll still say that those are equivalent. And so this also turns out to be an equivalence relation, and so let's prove it. Right, so let's fix 3 strings in my set. Well, what does it mean for A to be related to itself? I need the first 1 million strings, or 1 million characters of A to agree. Well, if A is the same string, then if A is equal to A, of course, the first 1 million characters will agree. So R is reflexive. Maybe just one minor point to add to the definition, right? It's okay for strings to have fewer than 1 million characters. In that case, we'll just say they're the same. If they have fewer than 1 million, we'll say they're the same if their characters up to that point are the same, right? So. Right, and so regardless, it's easy to see that this relation is reflexive. Symmetry is also easy to prove it in this case. So let's suppose A is related to B. By definition, that means that A and B agree up to the first 1 million characters. And well, in this sentence, I can just switch the role of B and A without changing the truth value of the statement. So B has to be related to A, right? So B and A have the same 1 million characters as well, and therefore R is symmetric. And so finally, let's try to show it's transitive. So let's suppose A is related to B and B is related to C. And we have to show that this implies that A is related to C. Again, if we unwind the definitions, the first statement says that A and B agree up to the first 1 million characters. And the second statement says that B and C agree up to the first 1 million characters. Well, if A has the same characters as B and B has the same characters as C in the first 1 million spots, then A has to have the same characters as C in the first 1 million spots. And so A has to be related to C. And this implies that it's transitive as well. So it's an equivalence relation. All right. And so one of probably the main role of equivalence relations in mathematics are as follows. So you have some set of interesting mathematical objects that you're working with, and you want to break up this set into different pieces of things which are equivalent to one another, right? So maybe there's sort of excess information that's getting in the way of whatever problem you're trying to solve, and you can deal with this information by grouping things together according to some properties, and then working with those collections independently instead. And so this is one of the main ways in which equivalence relations are used. Right, and so typically they'll be used to group. We'll have some set, and they'll be used to group elements of the set into different collections of equivalent elements. And each such collection will be called an equivalence class. And so let's give the formal definition. So let's say I have a set A with an equivalence relation R on the set A. Let's say fix an element A in this set, we're going to define the equivalence class. This is going to be called an equivalence class to be the set of B in A that such that A is related to B, right? So notice the order in which I write this doesn't matter because we're assuming it's an equivalence relation, so it's symmetric, so it doesn't matter which order I say. And so this set bracket A is going to be the collection of everything else in A, which is in the larger set, which is equivalent to A. Right? So the collection of all B, which are equivalent to A. Right? And so this set, which is a subset of A, again, using the notation bracket A with a subscript of R to indicate the relation, this is called the equivalence class of the element A with respect to the relation R. Right, and so again, the equivalence class is just the set of all other elements which are equivalent to A. Right, so not everything in the larger set may be equivalent to A. There is some number of elements of A which are equivalent, and those are the equivalence class. Right, and so if we write it like this, say for this element little a will be called a representative of the class. And so why do I need to point this out? Well, notice that, let's say I have another element of my set B, which is equivalent to A. Well, then if I consider the class associated to A, that's going to be the same as the equivalence class associated to B, right? And this really just follows from the definition of the fact that that the relation is equivalence relation, right? So what does it mean for some element C to be in the equivalence class associated to A? Well, that means that C has to be equivalent to A, right? What does it mean for C to be in the equivalence class associated to B? That means that C has to be equivalent to B. But if C is equivalent to B and C is equivalent to A, then because of the transitivity and symmetry of the relation, it follows that A has to be equivalent to B, right? And so if I have any common element that's in the intersection of these two sets, where I'm using just the definition up here, then it follows that A has to be equivalent to B, and that means that A is in the class associated to B, and B is in the class associated to A. And so if you write this out using set theory notation, you can show that these two sets are the same whenever A is equivalent to B. Great. Okay. And so, right, so it's very common that the relation will be clear from the context. So often for the class associated to A, we'll usually just write bracket A instead of bracket A subscript R. If we happen to be working with different relations, or if in the future you happen to be working with different relations, then you may have to indicate you may have to use the R to sort of distinguish between the different relations. But when the relation is clear, we'll just use two brackets without the subscript, just to make the notation a little bit less complicated looking. Right. So what are some examples of equivalence classes? So we'll just be expanding on some of the examples from earlier in the lecture. So in the first example, let's suppose that I let A be the collection of all people that are living in the United States. And we'll use the relation from before where we say that A and B are equivalent if person A and person B live in the same state, right? And so let's fix some person A. What is the equivalence class with respect to this relation associated to person A? Well, the equivalence class is the collection of all people who live in the same state as A, right? So you fix some person who lives in the United States, they have a residence in one particular state, and then the equivalence class associated to that person is the collection of all people that live in that state, right? And so in this case, we can think of the equivalence classes as states, right? So my set A is the set of all people in the country. So the set A is sort of like the United States. And then the equivalence relation breaks up my set A into different classes. And in this case, each equivalence class is a state, right? So the different states are different equivalence classes. More precisely, they're subsets of the original set A, so they're groups of people who live in the same state. But abstractly, it helps us to think of this as like the equivalence classes are states, and the whole set A is the country. And so this is something worth pointing out, which we'll expand on a little bit in a few slides. So notice that different equivalence classes are disjoint, right? Because you can't assuming someone doesn't have a residence in two states, which legally they don't, right? I mean, you can own property in multiple states, but there's one that's your like main residence for tax purposes. So with that assumption, then the different equivalence classes are disjoint, right? So each person belongs to one and only one state, and this decomposes the country or the set A into smaller equivalence classes, which are disjoint. And so the second example will return to congruence mod m. So we saw before that if A is the set of integers and I use congruence mod m as my relation, then this is an equivalence relation. And so in this case, what is the equivalence class of an integer A? Well, it's going to be the set of all B that are congruent to A mod m. And so right, so we'll see a specific example in a few slides where I fix m to be a certain integer. So I'll come back to this. So these equivalence classes are typically called congruence classes mod m, and so these are very frequently worked with in abstract math and in number theory and pure math, and they're also very useful tools in computer science. So a lot of things involve working with congruences mod some particular integer. And so these are certain equivalence classes which play an important role in a variety of contexts. Unfortunately, we don't have time in this class to really talk too much about number theory or to talk too much about applications of number theory in computer science, although there is a whole chapter in the book, if you go back to chapter 4, about number theory, which I think will have some applications as well. And so if you're interested, it may be worth skimming that chapter at some point in the future, and you'll see why these equivalence classes are important and what role they play. Or if you take more math or computer science classes, you'll see more applications of this equivalence relation. Okay, and so going back to the first example on this slide, so remember that I pointed out that different equivalence classes are disjoint, and the equivalence relation basically breaks up the set A into different classes of things which are equivalent to one another, and these different things are disjoint. And so mathematically, such a decomposition is called a partition of a set. And what we're going to see is that when you have a set A and you have an equivalence relation on that set, then that equivalence relation always breaks up the set or partitions it into disjoint classes, which intuitively may make sense, but we'll also prove it. So first, I want to make sure that we get all the definitions straight before we dive into the proof. And so let's have let's fix some set A. So a partition of a set A is a particular decomposition of the set into a union of subsets, right? So notice that each AI here must be a subset of A if A is the union of these, such that the AI are pairwise disjoint, right? So this means that if I does not equal J and I have two sets that are composing the partition, that they're disjoint. So if I look at the intersection, they're empty, right? So let's suppose we have a set A and we have an equivalence relation R on that set. Then if we consider the different equivalence classes of the set A with respect to the relation R, then these form a partition of my set A, right? So I'll have some given set and some relation on this set. And if I consider the equivalence classes separately, then if I look at the distinct equivalence classes and I take the union of all of those, then I get my whole set A. And moreover, the distinct equivalence classes are disjoint. And so one way of writing this is that I can write my set A as the union of all the different equivalence classes. And moreover, if I know that some element A and some element B of my larger set are not equivalent, then their equivalence classes are disjoint. Right, and so if you look at this piece of notation here, I'm saying A is the union over all elements of A of the respective classes. Well, it's certainly the case that many elements of A may belong to the same equivalence class, and so I may be having that repeated, that class is repeating in the union. Of course, so for taking union of multiple sets, if you repeat a set more than once, it doesn't change what the union is. And so the best way to think about this is more, I'm taking the union of distinct just distinct classes. So this object mathematically is the same as if I were to take the union of distinct equivalence classes. And so the point is then that those distinct classes, when I take their union, I'll still recover the whole set A. And moreover, those distinct classes will be disjoint. And so that will connect it more to the definition of partition we just saw previously. Right. And so how do you prove this? So the first thing to prove is just that I can write my set A. I can actually write my set A as the union of the different equivalence classes. And that's a straightforward set theory exercise. Right, because if I have any element of my set A, there's going to be some equivalence class which it belongs to. In particular, it's equivalent to itself. So it's at least going to be, there's at least one, I mean, there's exactly one class it belongs to. And therefore, A is a subset of this union, right? Because anything in here will belong to one of these classes, so A is a subset of this union. On the other hand, by definition, each of these classes is a subset of A, and so therefore this whole union is a subset of A. And so since each of these sets is a subset of the other, they have to be equal. And so therefore the main thing that we have to show is that if I have two elements of A which are not equivalent, and so this will be the notation we usually use for A and B being not equivalent, just the equivalence with the dash through it. So we need to show that if we have two elements which are not equivalent, then their equivalence classes are disjoint. Meaning if I look at the intersection of these two classes, then those are empty. And to do this, we'll use something called a proof by contradiction, which I don't think I've actually, even though we've been doing this for a while now, I don't think I've actually used an example of a proof by contradiction in class. And so how does a proof by contradiction work? Well, we're going to assume that A and B are not equivalent, but we'll also assume that there's some common element in the two different classes, right? So we're going to assume that this is false and that the intersection is not empty, even though A and B are not equivalent. Right, so let's suppose that I have some element C, which is in the equivalence class of A and also in the equivalence class of B. So by definition, C has to be equivalent to A because it's in the first class, and also C has to be equivalent to B because it's in the second class. But remember that this relation is symmetric and transitive, and therefore this tells me that A has to be related to C by symmetry, but then since A is related to C and C is related to B, by transitivity, that would imply that A is related to B. But we're assuming that A is not related to B, and therefore this leads to a contradiction. Right, and so it follows that there can be no element in the intersection, and so the intersection has to be empty, and so the two classes are disjoint. Right, and so that's what we wanted to prove. Okay, and so we'll finish the lecture today just by looking at two examples of particular partitions that are given to you by equivalence relations. Both of them will again relate to earlier examples from the lecture. So in the first example, we'll use this relation. Again, A will be the set of all residents of the United States, and the relation R is defined. A is related to B if and only if A and B live in the same state. And so as we saw before, we can view. Right, so if I fix a person A and I consider all the people that are equivalent to A, that's just going to describe the residents of a particular state. And so for this example, the equivalence classes are different states. And so I can decompose my set A as the union of the 50 different states, and the states are disjoint, right? So resident of New Jersey are distinct from residents of Massachusetts or something like that, right? So this does form a partition. Decomposing A as a union of the different equivalence classes. And so for the second example, we'll look a little bit more about this number theoretic relation, congruence mod M. And so for example, let's suppose, right, so my set will be the integers, and let's suppose R is the relation congruence mod 7, right? So two integers will be equivalent with respect to this relation if and only if their difference is divisible by 7, or more succinctly, if and only if A is congruent to B mod 7. And so the claim, well, the theorem tells us that the different equivalence classes will partition the integers into distinct classes. And so the claim is that actually the set Z is going to be partitioned into only 7 equivalence classes. Right, and in fact, the classes are those associated to 0, 1, 2, 3, 4, 5, and 6. Right, so well, why is this the case? Well, I just listed the equivalence classes associated to the first 6 integers starting at 0 and increasing, listed in increasing order, first non-negative integers. Right, and so if I look at any pair of 2 numbers from among these sets, you can see that they're not related to one another, right? For example, 5 minus 3 is 2, which is not divisible by 7. 6 minus 1 is 5, which is not divisible by 7, and so on. So each of these 6 distinct numbers certainly induces disjoint equivalence classes, because none of the numbers from 0 through 6 are equivalent mod 7, right? Or congruent mod 7. Okay, and so what we need to show is that there can't be any more classes. And so let's just start with the next number in the list in increasing order. So let's look at 7, which is right after 6, right? Well, 7 is a multiple of 7, right? So 7 will be congruent to 0 mod 7, because if I subtract 0 from 7, then I just get 7 again, which is of course divisible by 7. If I move on to 8, well, if I look at 8 minus 1, which is already represented here, then 8 minus 1 is 7, which is divisible by 7, and therefore 8 is congruent to 1 mod 7. If I move on, well, 9 minus 2 is equal to 7. Right? 9 minus 2 is a multiple of 7, so 9 is congruent to 2 mod 7. So 9 will belong to this class, the class for 2, and so on. So 10 will belong to the class represented by 3, 11 will belong to the class represented by 4, 12 will belong to the class represented by 5, and 13 will belong to the class represented by 6. And then once I hit 14, well, 14 is just a multiple of 7, so it will belong to the class represented by 0, and then this will keep repeating, right? And so even though the integers have infinitely many elements, right? So even though in this case my set A has infinitely many elements, this congruence relation breaks it up into finitely many different equivalence classes. And so it turns out one of the reasons this relation is so important is it turns out you can do basic algebraic manipulations with these different classes. Like you can add different congruence classes and multiply them and subtract them and so on. And so this is, again, something you would see if you took a number theory class or computer science where number theory is applied, or like an abstract algebra class. This will be talked about in more detail, and you'll see some applications of this construction. Just sort of very briefly, what's one way to think about how how it makes sense to add different equivalence classes? Well, you can think of this like it's sometimes called clock arithmetic, where, right, so let's say I have 4, I'm starting at 4 and I want to add, let's say I start at 5 and I want to add 3 to 5. Well, I add 1 to get to 6, and then when I want to add 2 more, but if I add 1, then I get to 7, which brings me back to 0. And then if I add 1 more, I should go back to 1, right? So you would expect that 5 plus 3 is going to be 1, right? So you sort of add the numbers like you would add hours when you're looking at a clock, right? You don't have to worry about that for this class. I just wanted to point it out briefly. Okay, and so that's it for today. We'll pick up with, I think this is basically everything we wanted to talk about for chapter 9. So the next lecture we'll begin talking about graph theory.